Hello, my name is Marlo Evangelista from University of the Philippines, Diliman. Today I will present to you our paper titled Scalable and Sustainable Community Networks for Inclusive Smart Cities. Smart cities require people to be interconnected. However, the digital divide, manifested through the unequal access to the internet, remains a problem not just in rural but in urban areas as well. It is in this context that community networks like Gwifi.net continue to be an interesting proposition in addressing the issue of internet access. However, the grassroots-oriented nature of these networks presents a different challenge. There is a shortage in supply for material resources and specialist skills needed to plan, establish, operate, and sustain community network. In order to address this challenge, we are proposing two design goals worth considering at an early stage of community network conceptualization. These are scalability and sustainability. Scalability refers to the ability of the community network to expand either horizontally, meaning it can accommodate more participants, there is a greater usage, and there is an increase in performance quality. Or it can expand vertically, meaning new and useful services can be introduced. On the other hand, sustainability refers to the ability of the community network to assure continuous operation, management, and growth. These two design goals motivate our basic technical question. Given all the challenges in which community networks are situated, can an open, software-defined approach help build a scalable and sustainable community network? This paper describes our effort to address this question. Specifically, we wish to explore whether an open and software-defined approach would, number one, ensure better interoperability among devices, meaning new participants, whether permanent or transient, can easily join the network. Number two, enable rapid deployment of community or externally provided services. Number three, have a unified view not only of the network but also of users and community-owned and managed devices as well. In a way, we are sharing the motivation, technical design principles, and initial experiences we learned from our previous work, Bayanihan.net's community network, and somehow evolve it by applying open and software-defined approaches. By the way, when I say open, I am referring to both hardware and software platforms with publicly available and extensible sources, codes, designs, and abstractions. On the other hand, software-defined encompasses a wide range of approaches, either control and data plane logical separation, network programmability, network function virtualization, network slicing, and other similar technologies. In the next few slides, I will discuss our design approaches for community network deployment. The first design approach is choosing the IP addressing scheme. We wanted to give members not just internet access but also visibility so they or their services can be reached not only within the community network but from outside as well. However, it is neither scalable nor sustainable to provide internet routable IPv4 addresses to household CPEs, especially when the community has a limited number of internet routable IPv4 addresses. Why not use IPv6 instead? Not only does it have a larger address space, but we can also give internet routable prefixes even within the community mesh itself. This will allow community members to host services for their own use or for the benefit of the community. Example of these services could be IoT-based services or even public safety IP-based CCTVs. To ensure that we can interconnect community mesh in sort of like a plug-and-play way, that is, without the need to configure addresses and routes explicitly, we use BMX6 as the routing protocol. BMX6 also supports address auto-configuration and UHNA to advertise IP addresses and internal home subnets. Of course, at the option of the user. However, not all end devices, sites, or even services on the internet fully support native IPv6 yet, so support for IPv4 is still needed. Also, some home users would still want to keep whatever RFC 1918 addressing schemes they have at home. So, to allow users to join without the need to change their address scheme, at the same time support IPv4 only sites and services, we use 464 XLAT transition mechanism. With it, we can allow traffic traversal over the IPv6 only community mesh and provide address translation services like PLAT at gateways to internet uplinks. However, in order for PLATs to work, community network needs a pool of internet routable IPv4 addresses first. This is also a challenge because it might be too expensive to apply for membership and IP resources from internet registries. Also, that membership might even require legal entity in place, which may not be possible for starting community networks. On the other hand, this might become a motivating factor for community networks to buy transit internet access in bulk. Community is, as far as we know, in better position to obtain concession in this way. We also believe that as IPv6 adoption increases, the need for larger routable IPv4 pools for PLAT will decrease. The next design approach is the concept of open platforms and open access. We believe that the use of free and open source platforms whenever possible is desirable for two reasons. First, it promotes uniformity and interoperability in deployed and managed platforms. This will in turn enable more collaborators to help maintain the network. Second, it promotes community participation in design and configuration decisions, where configuration settings and services may be published or reviewed in a transparent manner. This is in contrast to the closed and often secretive nature of CPEs from commercial providers. In other words, we believe that open platforms will help democratize access and participation in community networks by lowering the barrier of entry that might otherwise be imposed by standardizing to a single proprietary platform. Speaking of platform, the one we chose for this approach is OpenWrt. OpenWrt APs may natively support IPv4, IPv6 dual stacks, 464 XLAT transition mechanism, and BMX6. Community members may easily reflash their commercially available compatible access points to OpenWrt. From our experience, however, not all commercially available models are guaranteed to work with OpenWrt. So, sharing experiences and information regarding the availability of products are very important. Another approach is our position for accessibility. We believe that open access may be a worthwhile, if not an altruistic design goal for the community. An example of this open access design is, say we want to give internet or community service access to visiting or transient users. However, permanent users have concerns for capacity. Then, lower than best effort QoS may be provided. Finally, another aspect of our design is the use of programmable, virtualizable hardware both at the core and at the access side. Network function virtualization may be used to address issues of compatibility, promote cost sharing, and resource pooling at localized scales, and allow dynamic allocation. In the next few slides, I will discuss the application of the design approaches I mentioned before. This is done to evolve our previous work, Bayanihan-Nets. To give some context, Bayanihan-Nets focused on mechanisms to incentivize participation in community-based sharing of network resources. Our current work, however, evolves Bayanihan-Nets further by incorporating the design principle into its new architecture. This figure illustrates the evolved architecture. While maintaining the original features of Bayanihan-Nets, such as lower than best effort basis for subscription sharing, we have added new features such as IPv6 backbone, the addition of PLATs and CLATs through the use of Joule and BMX6. Also, to ensure support for Joule and BMX6, we require OpenWrt platforms. While it is straightforward to draw up the architecture based on the design goals, the mapping to a compatible, locally available, and affordable platform was another matter. From our experience, conflicts can arise between prices, performance, and so on. So, we made sure that prior to the deployment, a component selection process is needed to test candidate platforms. Since OpenWrt support was a requirement, we searched for the cheapest locally available open-world-based device. We initially settled for an outdoor Wi-Fi meshing platform which we named Platform A. After installing the needed components, we placed it as device under test in a simple scheme: traffic source, DUT, traffic sync. The goal is to see what performance the users of Platform A would expect as CLAT device. Our test consists of generating TCP traffic using iPerf3 while letting it seek a steady-state throughput based on the bottleneck of the line. Our test showed that when pure IPv6 flows along the CLAT device, there is an insignificant drop per flow throughput. Compared to when IP traffic flows, there is an observed 50% drop in per flow throughput relative to IPv6 flows. In Figure 2b, we see a linear increase in TCP retransmissions as the number of flows increases, which indicates packet loss or timeouts, although this is the expected behavior for flows contending for shared bandwidth. Given all of this, what does it mean in practical terms for users? It means applications that use a large number of connections like BitTorrent will have degraded per-flow performance beyond the fair share of bottleneck bandwidth. This will worsen with IPv4 flows, so users will therefore benefit if they use IPv6. Aside from CLAT functionality, Platform A was also tested as a mesh node. Although this test was by no means intensive since the goal was just to see if reflashing Platform A will have any effect on its performance as a meshing node. Table 2 shows that there was indeed some penalty, which suggests that further intensive tests would be needed for similar platform under consideration. Aside from Platform A popular commodity hardware, the Raspberry Pi 4, which can function as CLAT and BMX6 gateway and application end host, was also tested. The test showed that Raspberry Pi 4 can get users connected to high bandwidth services. For example, it can be used to enable students to participate in video conferencing and other remote learning activities. Clearly, between Platform A and Raspberry Pi, there are price-performance trade-offs when selecting a user access platform. Investigating it further, we perform price-performance comparison shown in Table 3 to help community members make informed decisions on platform selection. While previous results demonstrated the potential of the two low-cost platforms, a question arises: can we also find cost-effective solutions when we instead pool resources? In other words, instead of each household having to search for an affordable yet compatible device, would it make sense to deploy a more robust platform for shared use even at the access level? To answer this question, similar test was performed on a more robust platform, a server. CLAT instances were created using virtualization on that server. Our test showed that there is no significant performance penalty when the virtualized CLAT performs translation for IPv4 flows compared to IPv6 flows with no translation. This shows that virtualizable and programmable hardware at the access edge has potential for resource sharing and provisioning. As a note, devices used as gateways connecting to the mesh or as a mesh node themselves must support jumbo frames with MTU sizes above 1500 bytes. For our last test, we look at the provider-side address translator or PLAT. As the community network grows, the rate at which IPv6 addresses are presented for the PLAT will also grow. Therefore, there is a reasonable concern for the scalability of this function. To determine the impact of an increasing number of flows, a candidate PLAT platform was tested using iPerf generator and sync machines with 10 gigabit Ethernet network cards. Our test showed the potential of the candidate platform. However, this should be validated by scaling concurrent flows and using a mix of packet sizes that better model the actual internet traffic, which we have not yet performed. Finally, I would like to show a few scenes from our deployment sites. We applied the architecture in 2 residential housing clusters near our university campus. We provided several platform A's so that this can be further tested for real-world usage. Aside from the local community Wi-Fi roaming service, we also have support for Edge Roam. Top left is the satellite photo of one of the 2 deployment sites. Top right is the installation of fiber optic uplink for the community network. Bottom left is the screenshot showing the local community Wi-Fi, while bottom right is the speed test results by one of the residents. To summarize, we presented a network architecture for community networks that stands on 3 design principles. Number 1, scalable, sustainable, and routable addressing. Number 2, open platforms and access. And number 3, programmability and virtualization from access to core. Platform search, qualification, and testing will be challenging tasks for community networks. Even so, such an activity will be useful towards achieving technical scaling and sustainability and promoting cost transparency and informed platform choice among users. This is the end of the presentation. Thank you for listening.